I'm Thomas Yale, and for those who don't know, I'm the developer of Discovery, a software which analyzes English text. It performs natural language processing, a branch of artificial intelligence which attempts to enable computers to understand natural languages such as English, at least as far as understanding applies to computers. In its present form, Discovery is a core technology or methodology for analyzing individual sentences. Discovery is a stepping stone to other software that uses this technology for practical applications. It's a lot different from large language models like ChatGPT, in that Discovery is completely rule-based. In that, Discovery does quite a lot of things that large language models can't and were never designed to do. In an earlier video years ago, I described how I dealt with the problem of part-of-speech tagging. That's where a computer program attempts to figure out which part of speech of each word applies in a sentence and tries to figure out its grammatical structure. For example, break can be a noun or a verb, but used in a sentence it is either one or the other. In the sentence, I broke my foot, it's a verb. In the sentence, I'm taking a break, it's a noun. Discovery is different in that I approach the problem in a way analogous to a combination lock. The lock itself represents a sentence, each number disk is a word, and each number on the disk is a part of speech. The number of possible permutations equals the product of the number of parts of speech of each word. In I broke my foot, break is a noun or a verb, and foot is a noun or a verb. So the number of possible permutations is 2 times 2, or 4. Discovery uses rules to figure out which permutations result in a grammatically correct sentence. Sentences as long as 20 or 30 words, however, presented a problem. In earlier versions years ago, Discovery exhaustively tested them all. The longer the sentence, the higher the number of permutations until that number was astronomical, up to the tens of thousands. These sentences exhausted my PC's resources and Discovery crashed. That's when I decided on using dynamic programming to solve this problem. Dynamic programming is a set of techniques to solve problems by breaking them down into overlapping subproblems. That enabled the system to figure out which part of speech permutations applied to sentences without ever having to exhaustively test every one. Programming problems usually just use one dynamic programming method. The nature of this problem, however, required me to use both breadth-first search and depth-first search. Luckily, in so doing, it turned out that I gained the benefits of both. It accelerated the process of sentence analysis even more, and takes less than 1 second. Now I'm perfecting the problem of word sense disambiguation. Like part of speech tagging, word sense disambiguation is identifying the correct sense of a word in context. Many words in different languages have multiple meanings. For example, the word bank can have different meanings in the sentences I deposited money in the bank, and the boat went down the river bank. Words are ambiguous out of context, but in context, they aren't. Large language models compromise and attempt to resolve meaning out of context by proximity, or how closely words in a sentence or sentences appear next to each other, and in combination with others. Discovery, on the other hand, uses other types of rules to resolve meaning in context, as humans do. Again, like part of speech tagging, the meaning of each word in a sentence is determined by the meanings of the other words in the sentence. Here's an example. When John was a boy, he went to the bank to deposit money. A fire broke out on the first floor, trapping him above the icy river below the open window. Thinking quickly, the boy leapt from the bank into the cold water. Clearly, the intended meaning of bank relates to the building, not the bank of the river. The problem of word sense disambiguation will never be completely solved, since many words have meanings similar to one another, and others are vastly different. For example, in Discovery's vocabulary, which is derived from a lexical database called WordNet, the word bat could refer to a squash racket, a cricket bat, or any other club used for hitting a ball in various games. All 3 of those pretty much describe the same thing, but are vastly different from bat in the sense of a nocturnal mouse-like mammal that flies. Developers will always be pushing the envelope, but the situation is not at all hopeless. Some methods may be more efficient and accurate than others, and even then there are ways to deal with slight partial ambiguity. For years, I used existing rule-based methods to solve this problem, and then developed and experimented with some of my own. This latest method I've developed in actual testing appears to be the best of them all. Again, as complex as this process is, discovery still completes it for most sentences of any length in less than 1 second. The solution uses something called SUMO. That stands for Suggested Upper Merged Ontology. An ontology is a set of concepts or categories arranged in a tree-like structure. Child concepts are more specific than their parent concepts, and in essence, child concepts inherit from parent concepts. For example, dog, in the sense of a domestic dog, is categorized domestic dog, which in turn inherits from domestic animal, then animal, organism, autonomous agent, object, physical, and at the top of the tree, entity. SUMO encompasses most, if not all, possible concepts in human language: nouns, verbs, adjectives, and adverbs. And the developers of SUMO have mapped all the senses in all the words in WordNet to these categories. That's the basis of my solution. Discovery now looks at the rules it used to determine parts of speech and what grammatical functions they have, and thus grammatical structure, and then uses corresponding rules to compare certain words based on their meanings, figuring out which combinations of meanings would apply. Thus, in the sentence, "Babe Ruth hit the ball with a bat," Discovery would figure out that one rule would more immediately apply in which bat has meanings for artifact or device, which would of course make sense, and not mammal, which would make no sense. I generated rules in advance based on sentence frames already assigned to verbs in WordNet. This provides an extra criterion to make the process of identifying applicable meanings much more accurate, because it reflects how certain words are actually used. There are now just under 6,000 such rules. Right now, I've constructed a feature in Discovery which allows me to edit them and add new ones where necessary. I'm doing so based on the most polysemous verbs, that is, based on a list of verbs with the highest to lowest number of individual meanings. As a result, the rules have steadily become more specific and more comprehensive. At the end of this process, I anticipate that all the rules could be applied to any given sentence, and reflect far more closely how humans identify concepts of words in a sentence than any other method yet devised. The irony is that humans accomplish this with actual practice when they acquire a language as children, and do so without even thinking about it, while in computer programs this ability is horrendously complex and has to be intricately designed. Wish me luck.